For these kind of sessions, we're going to do pretty much every Wednesday from NZIP until just after Easter. Is to help people with the level 1 NCA. Today is about basically the energy external. Next week will be about the physics internal, just the SLOs. So we'll get going there. As you might have seen some messages, just to remind people of some messages, there are folders inside NZIP's secure site with resources. Last year's access is still allowable. If you don't have access into NZIP's secure site, basically there is an email that you can ask for access to get help for the level 1 stuff. And Matt McGovern is one of our 2 presenters this evening. Kerry Parker is on her way. And, well, they're going to be basically doing a presentation. After the presentation, we'll be having some time for question and answers. I'll be watching the chat during the presentation if you feel compelled to type anything in the chat and it happens to be a question that we can ask later. Or you can just, go old school and grab a dead tree and try to scribble on it and remember a question for when they finish. But we should have some time afterwards for question and answers. And I think that's about it. The recording for this will be available eventually inside NZIP, and we'll make sure word is spread around about that. So, with that being said...
Right. You see a slideshow?
Yep.
Yes.
Perfect. All right. So we'll get started. I am Matt McGovern. I'm head of physics at Havelock North. Kerry was on the team as well, and she is New Plymouth Boys High School.
Yep.
And we're just going to talk today about the development of these student learning outcomes and how we went about them, and what each one means, and hopefully helpful for you in developing your courses this year. We're building the ship as we're sailing it. So let's go. So the agenda for this is, I'll sort of quick talk about how we went about that development, and then there is 4 key areas for this standard. So the first one is this general idea of an energy toolkit. You've got all of these constructs that are going to be helpful for a scientific understanding of energy. So that's the concepts, the language that we've been specific about, and the types of representations. And then you apply that whole toolkit to the context of mechanics, electricity, heating and cooling. And I've said to Dave, or he said to you as well, while I'm watching this, it's going to be impossible to see the questions. So if you could put them in the chat, and then Dave could ask them at the end, and we can hopefully get around to them. So the actual development of the learning outcomes, there was a team of us that worked on it over the holidays. We had some people with international expertise as well chiming in and helping us. And there was a number of iterations as we went through this. And as we were going through and making sure that we were sort of adhering to the standard, we're also keeping in mind what does it actually look like in a classroom. So we're trying to put together learning activities as we're going along. Can this be taught in a classroom? Possible exam questions we were writing as well to make sure that these could be examined. And then whole unit plans as well. And so one of the big things that you come up against when you see the original standard is that if you're teaching 4 standards in science, or even 3, and you've got to divide that into the year, you've only got a number of weeks, maybe 6, 7, 8, 9 weeks to teach the standard. And that can be anywhere between 20 hours to 30 or 35 hours. It's not that much. And so as you see, and we talk about each of the student learning outcomes, we'll often talk about what's not included and what we've specifically not put there, because in terms of limitations of time, it's just not possible. If you are the sort of teacher that can get through things, just because things aren't student learning outcomes, it doesn't mean you can't still include them in your classroom practice. But in terms of making sure that there's continuity across New Zealand of what is possible, we've not included some things and included others. And then energy as a topic for teaching. There's a lot of research articles out there on best practice for teaching it. And the consensus is using this idea of energy, it's just, labeling things that, oh, there's kinetic energy in this, and now there's gravitational energy in this, and there's elastic energy in this. Energy is not very good at explaining things. It's not very good at explaining why things happen. The real strength of energy as a construct in science is in the law of conservation of energy, right? Comparing two instants in time, saying an initial and a final, and saying that the total energy here and the total energy here, they are the same. So it's a numerical law, and we want to make sure that we're getting the students to look at situations where they can compare the total energy before to the total energy afterwards. So and we'll get onto it soon, the language we've chosen and the types of representations we've chosen all lend themselves to that, to making sure that the focus is on the law of conservation of energy as opposed to just energy for labeling's sake. So that's the sort of the process and the thoughts we had behind everything. And so the first sort of area is this toolkit of energy, and it's called the concepts, language, and representations of energy. And so I'll go through each one individually. The first student learning outcome is the most important, which is the law of conservation of energy. It's the most useful, and we've purposefully set it as state the law of conservation of energy. Doesn't need to be explained any more than kids need to just memorize it as the most important thing. And it could be, and I'm not writing any exams, it could be that could be a first question on an exam, that easy for kids to get, sets them up, but it's important. That's what the law of conservation of energy is. As we move on,
if I put in here,
if you want, yeah.
my way of explaining it is that energy is like nature's money, and if I've got $50 and I go to the shop, I spend $20, I get something, but $20 has gone to the shop, it's now in the shop. And so when anything happens, there's some sort of energy transfer goes on. But lots of people would appreciate energy is not money is not a real thing. It's just a shared idea that works for us. And of course, we don't even know where our money is these days. So it kind of works quite well as an analogy. And the important bit, I think, is a lot of books will say that energy makes things happen. But energy is never the reason to happen. You can have $50 in your pocket and just walk around with it in your pocket all day, and it doesn't do anything. It hasn't made anything happen at all. So it doesn't have to make things happen. Things happen for a different reason, but energy is involved. So that's my way of explaining it.
Awesome, yeah. So kind of on there, I often talk about energy as this construct. It's this sort of, we've got this shared collective idea of what it is, and we want to make sure our kids get to that same point as well. And so the language we've chosen and then the representations we've chosen lend themselves to making sure that the kids are building the same mental model that we have. So if you look at these energy names, I don't think any of them are going to be any different than what you'd normally teach. But what we've done, and this is similar to a number of overseas curricula, is that these energy names are categorized into two categories. Now, previously, or in a previous life, I certainly would have, if you had asked me to categorize energy into two categories, I would have said there's movement energy and then there's potential energies. This is a different form of categorization. So the two names of them are forms and transfer processes. Forms are energy that's a property of an object. That's what I've written, and I've in quotation marks said energy that's inside an object. So you've got the picture of the ball there. And if you think about a ball and you take a picture of it and you say, what type of energy does that ball have? You can say it's moving, so it has kinetic energy. You can say that its position is above the ground, so it has gravitational energy. If it gets squashed, you can say it has elastic energy. It has temperature, so it has thermal energy, etc., etc., etc. So those energy forms are energies that an object that we'll deal with at, say, level 1 or level 2 actually have. Transfer processes are ways of getting energy out of that object or into that object, okay, or changing the total energy of that object. So work, for example, is how you might increase the total energy of that object. Heating, I might let Do you want to jump in, Kerry, with the difference between heating and thermal energy?
Oh yeah, well always a tricky one. So heating is energy going from hotter to colder, which happens by conduction, convection, radiation. So it's energy in transit. But the language we use around heat is so confusing, potentially confusing. So we, in discussion with the outside advisors, we're trying to use the word heating to emphasize its process rather than use the word heat, which can be a noun or a verb. And then for when something is hot and it's got lots of fast-moving molecules going on inside of it, then we call that thermal energy. The chemists would call it internal energy, but we've chosen thermal. So hot things have thermal energy, and when they spread that energy out to other things, making them hotter, they are heating them. And it's the language you're trying to use to emphasize those two different things.
Yeah. So you might be asking why we're categorizing these in these two different ways. One of the energy forms in the energy transfer processes, one of the things that comes up time and time again, and you can see it even in the pilot exam, there was a question on work, and you can see in the assessor's comments that the kids answering that question really struggle to connect the idea of work to energy. They can calculate it, force times distance, and they can talk about when work isn't done because the force and the distance are in different directions. And they know it has the same units as energy, but they're not quite sure how it ties into energy. Is it a type of energy? And so this is really trying to clearly differentiate those ideas and make it easier for kids learning it to see how it fits in. Work is how energy is transferred to something from another object when we're using a force. So if I'm talking about this jar, okay, I can transfer, if I'm just thinking about this jar at the moment, I can transfer energy into it by applying a force upwards. And now the jar has more energy than it started with. It has more gravitational energy. I applied a force to it. That's work. The energy of the jar increased. Energy transferred into it. So that's a bit of a difference. But it's the same names, it's just categorizing them in slightly different ways. But again, it's not new in terms of worldwide. The US is doing it with the NGSS. The UK is doing it. They've used different names. They use energy stores and transfers, but I think energy forms and transfers is the way to go. So that's the language we're going with. Representations which were suggested in the standard but weren't specified. There's two representations that I know of, visual representations for energy, and it's the Sankey diagrams and energy bar charts. And again, a lot of discussions were had. Sankey diagrams are really useful when you've got complex systems and you want to show many, many different inefficiencies. They're useful for, our national grid, where all our energy comes from, where it's all going. In terms of teaching the basics of energy bar charts have an advantage. They're really, really simple. They force kids to think about an initial and a final point without thinking about what happens in between. Okay, so that's the thing with energy. We don't really care what happens in between the initial and the final state. And they're easy for kids to draw, even freehand. So we've always found trouble with kids freehand. If you set an exam question on Sankey diagrams and they're trying to do it freehand, it's very hard to make all of the arrows the same width in terms of trying to show conservation of energy. So in terms of teaching energy as a construct, energy bar charts definitely have an advantage, and so that's why they've been specified. There's going to be another talk in a couple of weeks on energy bar charts, and we've got already a whole bunch of worksheets ready to go. The great thing about energy bar charts is you can get kids to show numerically that they understand the law of conservation of energy. So in my example there, you can see I've got 5 energy bits of gravity or gravitational energy turn into or become 5 bits of kinetic energy for this ball. The total energy of the system is conserved, right? And without something like this, if you were asked to do this numerically, you'd have to go into equations. And we know at year 11, the kids do struggle with the half mv squared and equating it to mgh. And so this is kind of an intermediate between just learning law of conservation of energy off by heart and actually doing some harder calculations. I can still ask merit type questions with just an energy bar chart, and numerically the kids only have to be able to add to 5 to be able to access it. So it's a really good way for general science kids to be able to access some harder, well, some important physics concepts. And these last two in this first category, I don't think will be a surprise. Power is just the rate that energy is transferred. And efficiency, we made sure that if we're going to be talking about it, or if there's going to be a calculation for efficiency, that you should be able to do it both using the energies, or if you've got powers instead, you can do it using powers. So that's the toolkit. You've got this language, which is all the energy types. You've got the law of conservation of energy. You've got representations, which are the energy bar charts. And then you've got these other concepts as well. So then we apply those to the concepts, the context. So Kerry's going to do the first one, and she's going to talk about what's in and what we purposely left out, and then I'll do the next one.
And so we're up to, so have we done the applied to mechanics? We're on slide 8? Yes.
Yeah, everyone can see.
Yeah.
Yeah.
So obviously the standard has got half mv squared, and so we can do calculations around that. And the there's a very strange sort of lack of deltas and changes in the standard, so we just kind of do a broad brush over it, I guess. But the so the 3 equations that are on the slide, half mv squared and mgh or delta h, and work is force times distance, allows us to ask the excellence level sort of questions, where they have to kind of work out how fast the ball's going when it hits the ground, at the instant it hits the ground, and things like that. But the emphasis is very much on the stuff that's more in the energy bar chart area, so the kids can access the concept without getting bogged down in the maths. So applying it to mechanics, the tricky bit is probably work. And there's been a few people asking questions sometimes about carrying things around. A student carries around, if you carry a suitcase along the road, flat road, you don't do any work. Well, that doesn't seem right, does it? So we feel that it's best to stay away from humans doing things most of the time, just because of the complication of how muscles work and how just to exert a static force, we have to do work, and how walking is such a complicated mechanical exercise. So we'd recommend you try and work with just lifting things up and down, or possibly going, rolling up a ramp for doing work, or pulling something with a constant force. So trying to keep it really straightforward and simple, that something's going faster with work being done on it to make it go faster, things like that. I think that's pretty much it for the mechanics.
The other thing is, what's not, I'm used to teaching at year 11 an introduction to position time graphs, velocity time graph, to build up that understanding of motion. And then you do this, the old mechanics standard had forces as well. But the reality is, if you were to teach those things and all these other things that we're trying to teach for energy, it's just not going to be possible. So
there's no development of concept of force in here.
Yeah,
you just go, it's like how hard you're pushing it. That's it.
Yeah.
No Newton's laws.
Yeah.
It's just force is transferring energy by pulling something along, moving. A force moves, work's done, energy is transferred. That's it.
Yeah. Applied to electricity is the same sort of argument, that the standard's energy, and we can't change that. The focus is on energy. It's very hard to, in fact, I think it's almost impossible to explain, series and parallel circuits and the goings on in circuits using the concept of energy. So therefore, why would we try? And so what we settled on was electrical circuits transfer energy. They transfer energy from outside a system into the system, or they can transfer energy from like chemical energy in a battery to something else. And so we're thinking of, especially this electricity topic, it's a way to be practical, hands-on, but it's also very much tied in with the thermodynamics topic and tied in with the mechanics topic. So all of these electric components will be an elevator lifting something, or a ski lift pulling someone up a hill, or an electric kettle, or resistance wire in a beaker of water heating it up, as a practical you might do in class. So the focus is on that they really need to be able to measure the voltage and the current, and then calculate the rate that energy has been transferred, power equals VI. And that's what we could boil it down to, the simplest ideas possible. And so we've identified energy in forms of transfers in a simple circuit, state the definitions of voltage and currents in a simple circuit, and you've got the star there, and apply P equals VI to a simple circuit. So a simple circuit, it doesn't matter if it's AC or DC, right? If you're doing measurements on an electric kettle plugged into the AC, the kids don't need to know what the difference is in terms of charge flow for AC or DC, compared to if they've got a question, which is a DC motor or something that's lifting up an elevator. It doesn't matter in terms of, as long as they can figure out how to set up the voltmeter, measure those voltages, and measure the currents when needed, and eventually calculate P. So that,
and it doesn't matter if they're wired in series or parallel either, really, because you're thinking, because there are plenty of domestic things where things are wired in parallel to give you more power, and you like some hot plates, I think, are wired in parallel, so you can have them hot. You can have more than, you can have like a super booster or something going on, so you're getting more power from it. And just that it's wired in parallel doesn't really matter. You can just look at the current going in and the voltage across it, and bam, you've got the power of the circuit from V times I. I'm disturbed by the fact that it still says resistance in the standard, but it's just got it as associated formulae and examples of physical properties or behaviors. So we don't have to have it in. And with the SLOs being out, that's going to put a very strong steer onto anyone who is writing the exams. They have to fall in line with the SLOs now, as I understand it.
and you want to do thermodynamics?
Oh, right. So thermodynamics. Okay. So thermodynamics. Yeah, thank you. Racing through it. I noticed that Ben sent a question about, do we have to explain about kinetic energy of particles? Well, most schools would be teaching the simple kinetic model of particles from year 9 onwards, that the states, solids, liquids, and gases, and the particles move around more and more as they change state, and as they get hotter, as the temperature rises, the particles are moving more. So it's not too difficult to say, well, they got more movement. You could say that thermal energy is like kinetic energy on a nanoscale. The particles are moving around more, and so it's the kinetic energy of all those particles is the thermal energy, and the thermal energy per particle is like the temperature. So we just so you're just building onto that model that we've already used, and for the weaker students, they can just stick hold of that. Yeah, so I see Ben's comment there about internal energy. I only said internal energy because one of the teachers at our school who's teaching the standard for the first time in parallel with me, we were talking about the language, and he said, well, why are you choosing thermal energy? In chemistry, we call it internal energy. He's a chemistry teacher, but I felt that thermal was a bit closer to a sort of lived experience, and it's another word that people use for that energy. So we went with internal, thermal, but posh chemists would call it in.
You've muted out there, Kerry. Is it just me?
Sorry?
Oh, no, go ahead. Yep, there you go.
The equations and the definitions for specific heat capacity, which is C in the equations, and then latent heat, which is L. What students, the weaker students who can't do any maths should be able to appreciate is that when energy is transferred to something, temperature goes up, and or you can change state. So in my lab this morning, we had the kettle boiling. The jug kettle with the lid up was just boiling, wasn't getting any hotter. So what was happening to the energy? And so we could just start investigating the idea that the energy is going into breaking the bonds, and the water molecules are getting out into steam. For the brighter ones, they can use the equations, and I've made some videos with simple experiments you can do with students, which work really nicely. But those are people who never taught it before, because it's relatively new to the New Zealand curriculum. I guess it's been off the New Zealand curriculum for a long time, teaching these equations at this level for most teachers. I think, and the hard thing I find is trying to get the language right. So we talk about heating, and we talk about thermal energy. And if you find yourself saying heat, I think, hang on, have I got it wrong? So the most the standard stuff is conduction, convection, and radiation. I would try to encourage students to realize that all of these mechanisms are usually occurring in more or less depending. It's not like there's just one, unless you're talking about energy coming from the sun to the earth or something. But when my cup of tea is cooling down, what's going on? We've got a conduction, convection, and radiation is happening. And there's endless amounts of interesting project work students can look into with managing temperature, whether it's looking at what they wear when they go out on the hills walking and managing wind chill and things like that, or whether they are looking at designing houses and using double glazing. And the thermos flask, which is on the sheet. Just being able to look at that and try to avoid the word efficient without being very careful about what we use, how we're using it. So there's some nice little demonstrations that you can do looking at cooling things, wrapping them up in foil and looking at the rate of cooling of different surfaces and things.
So the representations, the graphs, the energy bar charts fall nicely into here as well. For kids to see that the total thermal energy at one instant in time is 4 bars high, and then a minute later is 2 bars high, and you've got to explain the energy has left the system, and that's what cooling down means. And change of state's another one that looks really nice in those energy bar charts to show that you need energy from the environment. When ice melts to water, it doesn't happen because the cold gets out. It happens because heat from the environment gets in and increases the thermal energy of the ice. So those are all of the student learning outcomes. NZIP have already got a folder up there, as Kerry said, has practical ideas, videos of the practical ideas, videos of the energy bar charts. When we put together these student learning outcomes, we made sort of an expanded document to explain things that might happen and problems you might get and ideas that we're thinking of. This is an example of that. So this is the example of the work one, and what Kerry was talking about a desk does no work when it's holding a book, but you know, this question that's sometimes asked, that students hold a book and they're told they're not doing any work, even though it's really heavy and they're getting really tired. And actually, that's not true, because the human body, the muscles are constantly contracting and relaxing. So we've got just little notes like this, and this is going to be uploaded, I think, as well. And Dave can correct me if I'm wrong, to the NZIP. So this is the expanded explanations. I've put together 4 sets of worksheets for the energy bar charts, so they're finished and they're ready to go up to NZIP as well. We're going to have a draft exam that you can use in your class as a practice exam, and then there'll be a separate one that'll be, you know, the embargoed one for as a benchmark, so you'll use it but not give it back till Labour weekend or whatever. But you'll have a practice one, a draft one, so the kids can practice something before that benchmark as well. And then the upcoming talks is what's going to be talked about. This is specifically from, I guess, from the energy one, and Dave, you can correct me if I'm wrong. But I think that's the order, and who's talking about it, and the other ones that the NZ are putting on are for 1.2, obviously, as well.
Yeah, the best list of the Wednesday physics sessions is basically on the government site, or the mini post that Helen has posted on the Facebook page. But yes, it's a smattering, because basically there's no way we could have planned every Wednesday how to hit both standards without messing up somebody's schedule. So yes, it's about half and half. This is the first one on the external. So we have a few questions. First off, thanks, Matt and Kerry. We have a few questions. Ben's already been answered, so I won't mention Ben's question. I'll go in order from the ones that I saw. Matt Maud mentioned, will NZQA use the same definitions as NZIP, or the physics teachers, with thermal energy versus heating?
You want to answer that? I mean, we've been asked by the minister to expand and make very specific learning outcomes, add specificity to the standard, and that's what we've done. And so I'm hoping that they will use that specificity in the exams. I mean, if you look at the actual standard itself, it certainly hasn't been through as thorough a process, I feel, as we've been through with these student learning outcomes. There's some phrases that sort of contradict each other, and they haven't quite got the meaning right. So I feel like if NZQA are wanting to be consistent year on year, they'd be using these. So I can't talk for them, and I don't know if there's anyone here.
I can put in my 2 cents, and I'm sure a few other people lurking in there. You can always turn on your microphones and chip in. The authors of the exams are physicists and physics teachers, and the definitions they use, one would assume, would line up to what you have heard today. That's my gut. We don't have a list of physics definitions for this standard, to my knowledge, but that might be another thing that might help non-physics teachers if that existed inside the folder in NZIP. That's just a thought.
So don't they, the SLOs with notes for teachers, we produce that document. Is that available for everybody now?
It will be if it's not already there.
Because at the moment, and that's where there's more expansion on what we mean by with those notes at the side.
If it's not there, it will be very soon, Kerry. Yes.
Yeah. So we've talked about things like wasted energy and useless energy.
I was just thinking an overt definition list.
Yeah.
So we also have another question from Hansel. So you mentioned what's not in the standard. You mentioned the distance, time, velocity, time, forces, Newton's laws, Ohm's law, all that stuff is not in the standard. And she was asking, so are we assuming that will be covered in year 9 and 10? My own response, and then I'll let you respond, is in this assessment, it's not under the umbrella of what is assessed. When it is taught and how it is taught is up to the school for those listed things: velocity, time, distance, time, forces, Newton's laws, such. But I'll let you guys respond.
Yeah, and you could argue what I'm about to say, but the majority of teachers and possibly the teachers here that are teaching year 11 science might not go on to be teaching the year 12 physics and year 13 physics. And so something like forces, for example, although it should be covered and covered well at year 11 previously with the existing standard we've already got, as physics teachers, we know we have to reteach it because it inevitably is not done well. It's not a scientific understanding of force. So I'm not too worried that something like forces isn't done in year 11. At my school, we're going to do an introduction to static forces in year 10. So they're going to have some chance of drawing vectors and adding vectors on a static object. And we probably won't go into Newton's laws, but we'll certainly be introducing some sort of vectors. It's not an ideal world that we've got. We're starting in the middle. These SLOs are almost like curriculum that we've been asked to form them for year 11, not knowing what's coming above and not knowing what's going below. Does that mean that the people who go on to develop the level 2 stuff and the year 9 and 10 stuff will take these into account? I hope so, but yeah, that's not a very good answer, sorry.
Yep. Matt Maud had a similar question. We'll skip over Alka's. I'll come back to your Alka in a minute. But will the external authors use the SLOs in their creation of externals? And that I've had that question for months, ever since the minister right before Christmas decided the SLOs needed to exist for each and every standard. So now we have SLOs that exist for each and every standard across the grid. The externals have been given to the authors and the NAF. One would assume that the people who write exams are using the SLOs as an expansion of the standard.
I mean, if you look at the pilot for this energy exam is up online. You can find it. It's just a little bit hard to find. Most of it is it's okay. It all meets the standard. But the problem is you would have had to have a crystal ball to predict what was going to be in the exam. And the way it's happened previously is that when NCA was first came about in the early 2000s, was those first 3 years were a disaster, and everyone was figuring out what was in the exam. And then after you had some continuity in the exam, you just use the exam as your curriculum. And I think this is almost a step before that.
Yep.
So now this is now saying, okay, we've got a group of experts to help guide the exam writers. Eventually, I think people will do the same thing. It'll be too many documents to keep looking up these SLOs, and people will just look at old exams. But at least we've had a chance as NZIP to be able to put some best practice in there and make sure we're sort of guiding it in the right direction before they go and write these exams. That's my interpretation. I could be completely wrong. I'd love to hear what NZQA say.
Well, I agree with you. I know that the NAFs and the authors are currently in process across many subjects of having discussions because they're just getting up to speed, basically. We have two other questions that are, shall we say, detailed and pedantic, but in a good way. The Elka's asking, would we include the concept of voltage is energy over charge at year 11?
The equation hasn't been put in.
Or the concept.
Yeah, the concept, yeah. But I mean, I can tell you, we didn't put the equation in because we didn't want it just to turn into another maths paper where the kids are just having to use formulas and just calculate things. But certainly, it's asked the kids to define voltage. And so any definition of voltage, usually that would use energy, is going to be good enough. So if that's the definition that you want the kids to understand a little bit about what's going on in terms of the potential difference, I guess, but certainly not the equation, because that would just be, I think if we have too many equations like that, it just turns into a formula hunting exercise. What I was trying to hint at with these energy bar charts is, you can get up to merit level questions without having to do any complex equations. And at year 11, we don't want to put too many kids off physics. There needs to be some maths because it involves maths, but it needs to be quite conceptual at that level as well.
So it's more for a definition than no. The other thing is the equations that are currently listed in the standard don't include efficiency.
No.
But efficiency as a concept is buried inside the language of the standard.
Mm.
So the SLOs sort of expand that out, is how I see it.
Yeah. And so with the further notes that we wrote about teaching electricity, we put explicitly that the emphasis is on the electricity transferring energy, and exactly how the energy gets from the battery to making the light come on is beyond a standard. And as physicists, we know that that's hellishly complicated. All we've ever done in the past is given them this little funny idea of Mr. Coulomb running around with this bag of energy, which isn't really true. But if you want to do that, and if you're doing that with your year 10s because you're teaching electricity, I mean, I think in my school, I'm going to really try and make sure that we're doing, in our year 10 electricity, it's emphasizing electrical safety. So people understand about overloading circuits and what to do if somebody has an electric shock and other things which are nothing to do with this course, but everyone uses electricity. And so you build on what the students' prior learning was already. So knowing that a volt is a joule per coulomb and that an amp is a coulomb per second, that means that if I multiply them together, I'm getting a joule per second. Bam! That's nice.
Yeah. But that example does live inside the year 12 physics current content. So yes.
So there'd be no harm in doing that if your students were okay with it. But it's the emphasis is on the transfer of energy.
Understood.
And P equals VI.
Cool. We have one more question that I've spotted in the chat. Yet again, a very good pedantic question. So thank you, Rebecca. The standard mentions the capital letter E for thermal energy, and all the physicists that I know use a Q. So do we have to be very conscious of the equations given to the kids having a capital E versus what you and I would use as a capital Q?
Yeah, I mean, they're different things, right? So the thermal energy, we don't have a formula to calculate the thermal energy of a glass of water, but we can work out how much it changes by, right? And that's what the heat. So Q is the symbol that physicists use for the heat, which is the transfer of energy in and out by heating.
There you go.
And so that wasn't in the original standard, right? And we've put it in. We're trying to be consistent
they had
with
the equations of E equals mc delta T and
Yeah.
E equals ml.
Yeah.
Rather than Q equals. Yeah.
And we did have a discussion.
I'd like to be a delta there in front of those E's, but
yeah, because the delta.
It's the same with potential energy, gravitational potential. They've got EP equals mg delta H. Well, what's that then?
Yeah, because you did mention that, Kerry. The lack of deltas in the standard it shows the authors weren't quite up to speed with the underbelly of physics.
And every now and then they've got a few deltas. We've got delta T and delta H, but the rest of it, all the other deltas, and just got forgotten.
But it's just something to be conscious of, that the given set of equations are listed in the standard. That's, I think, Rebecca's point.
Yeah. So I guess that's an issue that one says Q and one says E thermal, and either the ministry will change slightly tweak the standard or slightly change that SLO.
Yeah. As far as I understand, across the board, not just physics, the standards are locked in stone for some time.
Right.
Only immense urgent changes will occur. I think one occurred in the chemistry's explanatory notes last year. But it all depends on the definition of an urgent change. So yeah. So that being said,
the standard says associated formula, doesn't it? And it doesn't mean that they have to be given in the beginning. These are the equations you will need to use. I'm hoping that V equals I will quietly go away. And yeah.
No, it is. That's
That is
crystal
what
ball
it is.
reading, and all of us could spend a lot of time in Vegas trying to bet on what's going to happen. As Matt said, in a few years, the dust will settle.
Yeah. So I'm looking at down the meeting, the chat. Alka's summarised what I was saying.
Yep.
The heating's a transfer, it's Q. It's similar to work done W, and that's how it fits in. But yeah.
Exactly. Now, just being conscious of time, we've got a maximum of 10 more minutes. Does anyone on the meeting, we've got 45 people in here, are there any other questions for either Matt or Kerry or anyone else? You have to turn your microphone on if you feel. No? We'll do the standard waiting about 30 seconds. I'm having memories of Zoom quasi-teaching, waiting for students to say something. So I will thank, first off, Matt and Kerry for their presentation, and for NZIP, all the behind-the-scenes stuff, and to make those 2 folders of resources available to teachers nationwide. That is a growing resource that will develop as the term goes on. For people that are using term 1 to teach the content for this energy standard, if we didn't cover something that you urgently want, reach out to somebody inside NZIP. If you can't wait on the Zoom session that has those kind of things that might pop up. Similarly for the internal, if you look at the list of Zoom sessions and the internal is too late for you because of your calendar is set in stone and you can't move things around, reach out to somebody. Okay. A few of us have been answering emails since before the school year started. So that being said, I will stop the recording unless